Hello, everybody. My name is Gustavo de Morais. I am working together with Parallel Programming Group, especially in the area of performance modeling. That's what I want basically to discuss here today. And we also are using some LLVM framework to help us with our projects, and that's what I want to basically introduce to you guys today. In this work, I have here the list of collaborators, and this is also a collaboration together with ETH Zurich plus the Jülich site. And if you want have more details about this paper, it's currently under review, but you also can reach the full paper in archive, and please feel free to give us some feedback. And if you also feel that you can profit at somehow of our work, please just reach out. Okay, and that's basically the motivation for what you do performance, and you have a tool for performance modeling that is called XtraP. That's a work that is also in collaborated with the ETH Zurich, and you can find explanation link in this YouTube channel, which you can have access here. And XtraP is a performance tool to find out bottlenecks or performance issues before they occur. So basically, what happened is you have our HPC application where everybody knows here you have some sorts of computation communication. How, However, different characteristics can happen once you want to scale our application for big clusters. In this case specifically, the communication increasing a way higher than the computation. So you don't want this, and of course this problem has to be found way earlier during the develop side before everything is already running in cluster and getting a lot of energy, and you have to fix the problem before it occurs. And XtraP is a empirical performance modeling, so you need to have measurements. And another unpleasant surprise of this is the fact that when you go for the books and you study algorithm performance, you reach a chart that is a graph that with the data is like presented here with very clear expectation of performance, but when you go to the practice is not what it happens, because we do have noise and you do have a lot of things going on. And this is our challenge, that you have to look for data that looks like that, and you have to infer the right performance that come up from this. And this is our paper works with. So basically, this is more or less our framework. So starting here with the red chart, this is like the state of the art, how XtraP works. So basically you get a set of measurements, and these measurements can be time, energy, or anything that you want to model. You give into XtraP and it gives a performance modeling. That's basically represented here by this red line. And this is actually a real application that it took from Cryptic. However, our approach does something a little bit different. Before you go into the performance modeling, you first get in these noise resilient measurements. And for that, you include LLVM into our framework. So what are the noise resilient measurements in this case? Basically blocks for computation, bytes for communication, and then you try to reach everything. And you expect that these measurements can be representative enough of our application. So with that, you create some API inside XtraP, where you basically first derive priors and create hypotheses for the functions using noise resilient measurements. And once you have the skeleton of the function, you insert the noise sensitive measurements. And as a result, you have performance modeling represented here in blue. And one advantage of our approach is the fact that these noise resilient models aligns more close with the theoretical expectation of your code. And this is basically what you want to sell. So, okay, you have an application and you are giving a performance modeling that measures one time and is close for what you are really expected from your application. And okay, so the first step for make all this framework works is getting some noise resilient measurements. And we're starting together with Jülich to collaborate into XtraP to have like an extension of XtraP that supports LLVM. And once you have done so, what it does. First, for computation, you've created some LLVM IR representation of the code, and we'll make inserts of Scorpio instrumentations into the basic block level. So now instead of measuring the runtime of the application, you can basically measure it how many basic blocks will be executed. Of course, you do not measure all the basic blocks, otherwise the overhead will be way higher, but you know how to identify a loop, and you know which basic block you need to measure. So you have some filters, so don't worry, it's not the overhead is not that big. And of course, you also need some sorts of communication, and for that, you basically look for the MAPI characteristics and the skeleton, and now you know more or less how many bytes will be transferred. For example, in this application here, you know, just looking for the size of the vector, the size of n, you already can infer how many bytes will be transferred plus how many processes you are basically using in your application. Okay, having the measurements, the next step is to get some performance models. And this is more or less how XRP works. Looks a bit complicated, but it's a straightforward equation. So basically, you have an equation that can have some sorts of model candidates. So you have these predefined performance models where you basically insert some data and use some statistical measurements to represent the data inside this using these equations that you have preselected. And XRP can accept as much performance as you want. In this example here, I include like 4, but could be as much as you want, like process, problem size, solver, result precision, everything that you wanted, and you put all these performance equations independently, and you create models for each one by one, and then you see how they interacted. So they are totally independent. That's more or less the example that I have here, where you basically have performance models with m variables, and I can show here one example with a basic block model and with bytes models. So you can see that not all of the performance equations are being used in this equation, which means that they are not representing any influence in the performance of the equation. And for us, it's really important to use noise resilient measurements in this regard, because sometimes you start modeling noise and get a lot of performance equations that they are not supposed to be there, because the noise makes your model interpret something that is actually not true. And with noise resilient measurements derived by LLVM, you can have some models that are more clean and more correct in this regard. Okay, but you have a bit of problem, because before I mentioned that you can measure the number of bytes, but the bytes itself is not the only representation of an MPI communication performance. And here I have different set of equations that you basically took from the literature. And these equations are somehow more representative of the MPI communication performance that you want. And something that you can that I can show here is that I have one equation inside the big equation. So basically I have this performance skeleton, and I have to insert these new equations in red that are basically representation of how the bytes are scaling. Once everything is set up in this skeleton, I can have this sort of variables, which I have prior models, the bytes model, that is another equation, and a lot of different variables like input parameters, number of MPI ranks, a factor for latency that you do not know yet how much it is, but you have a representation for latency, a representation for bandwidth, and a representation for computational cost. So in the end of all this design, you have basically a skeleton of how your model is supposed to perform. However, I can give you a skeleton with basic blocks, a skeleton for bytes, but at the end, we understand that what a performance engineer wants is a model of runtime, because we want to see how much computational time your application will take. So this is basically our next step. So you have the noise resilient prior to define the performance equation, and then you input the noise sensitive data to fit this skeleton. So now is the time that you combine both noise sensitive and noise resilient data, and as a result, you have what you call here the software counter based performance modeling. And let me give an example of how all this configuration is supposed to work. So basically here I have like, maybe I should use a laser pointer, I think it'll be easier. Yes. So here I have like an equation with some sorts of some elements of communication and some elements of computation. And for communication, you have different times of measurements that gives different times of performance, like time, bytes transfer, the theoretical model for this specific MPI communication, the prior that you previously defined in our performance equation, and finally the noise resilient performance model that you want to sell in the final design. And the first thing happened for computation, where you have time, the basic blocks model, the prior that you define it, and once you put everything together, you finally have the noise resilient performance model for computation as well. And you may ask, okay, but okay, now I have the noise resilient model, so what I can do with that? And the answer is, you have some benefits coming from this approach. First, you can show that your model, you increase the accuracy. You have some models that are robust to noise, so you can have like more trust of how your model is supposed to perform. And also it will reduce the experimental cost. So basically, we did few evaluations to show that, and especially you did measurements and tests into Lichtenberg, plus the Eureka DC, that's a cluster from Jülich. You have some comparison baselines where you use our software counter-based model, the classic performance, which is basically runtime performance. And you also have a neural network, the noise application that was previous published that you also compare here in our code. And you want to use some metrics to compare these values. So basically the exponent deviation to see if the equations are diverging too much from the theoretical model. And also the relative error that is basically measuring a data into the test set and see how close you are for this. Which one can say that is not so reliable because the system has noise. So once you are using a test set, you have to also consider that your test set has noise itself. And it was a little bit tricky for us to evaluate under these conditions. So you introduce a benchmark generator that you created for this work, and now you are extended for new approach with new features and also support LLVM and has more approach than I'm showing here. But basically the idea of the benchmark generator is for you to create a code which you know the theoretical performance. So basically you create C++ kernels, which is basically a piece of code which you know how it's supposed to perform. Like here, okay, it's basically a for loop, and you have like this performance defined, this for loop, and you know it's supposed to perform like that. Another piece of code with another performance, and so on and so forth. Okay, once you have a lot of kernels available with different times or different kinds of performance, you as a user can basically define an input parameter, define the complexity that you want for your kernels, and then define how you want to make the composition of the kernels. And then you can have some code that is represented like that. For example, with kernel 1 that is basically defined by a MPI bcast with a vector, another kernel with this complexity. Kernel 3 has a nested kernel 4, and kernel 5 is basically a constant approach. And at the end, you make like a mix of codes, and our benchmark generator gives you, say, hey, you have elements of computation, elements of communication. This is the performance of this big mix of codes you have. And the idea here is basically, okay, now I can play with codes that have theoretical performance available. And you basically did 200 syntactic functions to analyze. And firstly, you verify the accuracy of these functions. And you can see that, okay, our models are using the exponent deviation. You can see that are basically equal to the theoretical performance. Okay, it's good. That's what we were expecting, but this is a way to show it. While the classical methods has some sort of variation around. And then for the relative error, okay, you get like 35% of error for computation, 60% for communication. Looks bigger, but again, you cannot really trust these measurements here specifically because I think you make a step that is way for the test that was way bigger for the modeling, and of course the error increases. But it's a good idea to at least show that if you use classic modeling, you can get like not better results. Of course, to prove the robustness of noise, you also include some artificial noise, where you basically show that even though our models has some sort of error in the relative error, you are kind of constant over the artificial noise, while the classical models varies, of course. And then the experimental cost. This is another characteristics of this approach because the standard modeling for XRP requires 5 different measurements per configuration to avoid noise. But since you are already avoiding noise by nature, you don't exactly need to do 5 measurements, just one is enough. So we basically show that you kind of reduce the cost without requiring a lot of measurements. Okay, one can say that the benchmark generator is okay, but it's not like a real application itself. So let's go for real applications where you have two ones here that is basically Cryptic and relearn. And you choose these two ones because the default paper mentioned that they have no theoretical performance, so you want to seek and see if it makes sense. And you did 2 measurements into Lichtenberg and Eureka with the parameters that I have here. And this is more or less how our accuracy graph looks like. So first of all, we have like a theoretical model that is basically from the literature for the each performance. You have a classic, you did one performance for cryptic computation, another for cryptic communication, and another one for relearn that you basically merge computation and communication together to have like a final model. And then, okay, you have the theoretical model, the classic that is basically find out by noise sensitive measurements, one that you remove the noise using deep neural networks, and finally our model. And the overall conclusion of that is, okay, our model is way closer for the theoretical expectation. And then you also show in real scenarios how our model looks like. So basically here, use the theoretical model in black, that is basically force the data to fit the theoretical model. The classic performance modeling in yellow, deep neural network in red, as the software counters method in blue. And you show here how you fit the data for the training model and how you use the test data. One interesting characteristic is that you see that the test data really varies here, as you can see in these points. However, you took the median values for all of them, and in conclusion, you have the same conclusion in the benchmark generator. Okay, our models are close to the theoretical expectation at the same time that are increasing accuracy, even though using like real data. Once you apply artificial noise, you also can see that the models really variated here for the exponent deviation. Sometimes getting like weird behaviors because it's random noise, so you cannot predict that it has like a linear increase, while you basically keep constant because the exponent deviation doesn't change. Our exponents are defined by the skeleton of the function, so you have no risk of variating due to noise. Of course, the relative error, you have a little bit of variation because you are still fitting the coefficient with noise-sensitive data. However, it's way lower than the classic model itself. And you also pointed out for the experimental cost. These graphs show more or less a sort of we make like some variations with the data, like with the models, considering like 1 measurement, 2 measurements, 3, 4, and 5, where you can see that usually when you increase the number of measurements, they increase the accuracy and the results getting better. However, our model basically keep everything constant without requiring so many measurements. And you can see from our concurrent methods, this is not true actually. Multiple measurements are interesting, especially in systems and clusters that are suitable for noise. Okay, I think my time is running low, so let me rush up for a conclusion. So basically, the conclusion is quite clear, I believe. So our method accurately captures the computational effort, and it's really close for the theoretical expectation, give you trust for your models. You reduce, if not eliminate, the need for multiple measurements because you are noise resilient by nature, so no need to do 5 different measurements for reducing noise. And under artificial noise, our noise maintain stable uh, rates, even though all the models basically breaks when you put like 50% of noise. Again, I invited everybody to read the full paper in archive. I also mentioned here some reference that I used during my presentation, and please, thank you. I'm very happy to get questions if you have so. And you also please take a look at our YouTube video for introduction, and you install and use XRP. It's quite easy and quite straightforward. All right, thank you. All right. Mhm. Okay, let's see. Let's. Okay, well, the question, if I understood correctly, the question was if I insert new instructions, new code, how I make sure that I guarantee that the basic blocks that are inputted into this code will be instrumented or will be excluded from the filter. Am I correct? No, honestly, no. You ask if the instruction that you inserted are interfere the optimizations of the LLVM IR, and the answer you didn't go that further. You basically find some structures like loops or if conditions, for example, that you try to not instrument everything for these specific instructions that you have like pre-organized, because for loop you have like 4 basic blocks, and when you basically only need to instrument in one. And once you recognize that, that's what you include in the filter, nothing something so more in the direction of optimization code. Yeah, welcome. I have another question, I believe. Yes, but you also support OpenMP. Sorry, I have to ask the repeat the question. Okay. Okay, if it's also working for other benchmarks as Cisco, different than API approach. The answer is I need to check. What I can tell you is that you support CUDA, you support OpenMP, and you support MPI. But you kept in this design, even though in our paper itself you only explore MPI configurations. But I have the feeling that it won't be a problem once it works correctly to a SCORP framework. What I'm telling you is I cannot guarantee because I didn't do, but I believe so because once it's into a SCORP, it's supposed to work. Okay, the question is if the code works for C++, however, if I only have LLVM IR representation, if that works like similarly. The question is yes, it works similarly for LLVM IR because you're basically starting making the test with LLVM IR itself before you go to SCORP. The problem is because you didn't make it like publicly. You basically put everything into SCORP once everything was done and say this is what you want to sell and this is what you publish it and make free for the community. However, in the background, you make tests with LLVM IR. If it's interesting to you using IR, I can talk to my colleagues to make it public. Mhm. Yeah, I would be happy to talk more about that if you want, because maybe this is something that I can include in the benchmark generator new versions, the new versions that are creating. So if support your case, it's better because you make something that is like more applicable for everybody, which people can use and make us happy. Thank you.